And so today is a discussion with a couple of presentations on IR issues, and in particular connecting those to also observational questions or matters. And so we'll start with Martin Slot.
Yeah, so I thought I'll just say a little bit about what I think might be an interesting conceptual effect and an interesting observational effect, and how those might be related. And I guess that's a point for discussion. So if we consider the ADM metric and then consider the spatial metric, sorry.
You said if we consider the something,
the ADM metric.
ADM metric.
Right. And then consider the spatial metric within that. Then we usually write it as something like this, right? So the question concerns correlators of zeta and gamma, where zeta is the scalar perturbation and gamma is the tensor perturbation. And so it's a very kind of well-known thing that as gamma becomes long labeling mode, means that the Fourier mode of the tensor mode becomes much longer than the size of the horizon. The mode becomes classical and freezes, and basically one can look at it as a classical perturbation of the geometry. And in Fourier space, that can be captured by a transformation of Fourier momentum. I just quickly here to say in order. And this is useful because this is what has been used to calculate many useful things, including expressed divergences. So if you, for instance, consider the two-point correlation function, as has been done by Nardesina initially, in the background of this classical calculation of the geometry from this long tensor mode, then this two-point function is the tree level one without the presence of the long tensor mode, and then we can expand in the long tensor mode using this. This is something. It's not so the details is not so important, but let me just flash some of it. No. Anyway, there's something like this: kk, dk squared, zeta. So there is a derivative in the momentum, and then to next order there is a term which is something like this, schematically, which is the square of this derivative.
Martin, there's a microphone for you.
Sorry? Okay. So, sorry. So basically, this is just the expansion to second order in the tensor mode. So we have the first order and this two second order things here.
Could you explain? I really didn't know what you meant by that arrow k squared goes to. In what sense does it go to that? What are you talking about?
So if you view if you have some long labeling perturbation of the tensor mode, then it looks locally as a classical perturbation of the geometry. And if you view that perturbation in a Fourier momentum sense, then you can expand it like this.
So you're using the non-Gaussianity calculation.
Talking about a WKB approximation?
Think of gamma as a constant. And there is the momentum defined with respect to the coordinate that appears in this metric, and the momentum where you absorb the gamma inside the coordinates. And the relation between two momenta is what you got there.
So does this assume the perturbation is small, presumably?
So yeah, the expansion here assumes that it's a small perturbation. Right?
So it doesn't apply, for instance, to the case of most interest, namely eternal inflation.
So early inflation, you mean something like eternal phase of inflation? Or
Eternal
something?
inflation.
Yeah. So okay. So well, it doesn't. Well, unless one is able to resum it as series like this, it doesn't apply, right? I mean, so. But the question is whether one is able to do something like that. I guess is an interesting question. So.
little be known about that, or how would you?
Well, I think I will try to explain something, and I will, at some point I will reach something which is like some sort of renormalization group equation, which may shed some light on what you light on what you're saying.
Leonardo was saying that they have some
Leonardo was
characteristics of-
sidestepping the issue.
Well, Well, they had some characteristics of the eternal phase.
Oh, yeah, but that is not
Not the full function.
not in
So,
this
yeah,
way.
so, well, I'm not going to address it directly. That's true. In any case, so the point here is just that just to remind you that this kind of trick has been used to calculate the Nardasina consistency relation. Right. So what he did was to look at the limit of a long wavelength mode. Okay. So we look at the limit where the wavelength of the tensor mode goes to 0 in a correlator of this sort. Okay. So a tensor correlator with scalar modes. Okay. And the nice trick is that you can just view this as a classical kind of averaging, because this is now a long wavelength mode, so it's like totally classical. So you can view this as an averaging of this mode in the background of long tensor modes. So something like this, okay? And then, of course, detailed calculations, which was performed using the in calculation, verifies that this is exactly true in this limit. So similarly, one can. So this is a diagram where you draw something like this, right? Something like this, okay. So similarly, okay. So this comes from the linear term, right? This comes from when you multiply here, you pick up the linear term here and you average over. Similarly, you could look at a 4-point function. So you could look at something like this. And then similarly, you could look at this in the limit where you have okay, you can look at the contribution from the exchange of a graviton. And you can look at in the limit where the momentum of the exchange graviton goes to 0. So something like and then you can use a similar trick. You can say that this is basically the correlation of two pairs of scalar quantas along a long wavelength classical mode. So we can again write this as something like something like this, okay? And also again, detailed calculation shows that this is really true. Okay, this is how it goes. So it was something I did with Siri and Vanity, okay, in 2008. So at least to this level, it really shows that you can capture the effect of this long wavelength and at this point classical perturbation of the geometry in correlators by doing some classical averagings like this, okay? And then for the loop, again, you can do something similar. So now you basically just say that, well, I want to calculate something like this. Sorry, let me take a scalar one. Consistency. Okay, I want to calculate something like this. So I want to calculate the loop contribution. I want to calculate the IR contribution, okay? So then I can think of this as basically being, again, my short scale correlator in the background of the long wavelength classical modes, and these soft graviton modes can then be their effect on the 2-point correlator can then be captured by averaging over all the soft modes. Okay, so this is basically like if we are in like a box and we want to calculate a correlator of some short modes, then we are averaging over all the soft modes which fits inside the box. Okay, so this is equivalent to averaging in some sense over a volume in which we are calculating this average quantity. Okay, and then it's no secret that this one goes like, well, it has two contributions, right? There are two second order contributions here that won't vanish when you take average. The linear one, of course, vanishes if you take the tab total vanish. So there are two contributions that doesn't vanish. And the two contributions has been shown to match exact Feynman diagrams. So these are the two contributions. This is the infrared part. These two contributions in this procedure gives you the infrared part of these two Feynman diagrams. Okay, and it's proportional to something like what will be something like h squared 1 plus 1 squared with something like this, right? Okay, there is a coefficient here that depends on the tilt of the spectral index and all that. Okay, but the main point here is that there is the Graviton variance appearing, and hence this correlator has a logarithmic divergence, which goes something like some cutoff or some IR cutoff or some UV cutoff, which is actually because this is a classical argument. The UV cutoff will be given by the scale at which we can treat the modes as being classical. So that's basically horizon exit. And then the IR cutoff in this picture is given by the volume over which you are averaging.
So this is just a loop part, right?
So this is basically a one loop. Okay, this is the one loop part. So this is like expanding to this order.
And why is it only the long wavelength gravity modes that?
Oh, there is also I just chose to calculate the effect of the tensor mode,
okay.
But you can do the same for the scalar mode. It's no difference. It's just I just thought that it was nicer with the tensor mode. But okay, I mean,
See, Martin, if epsilon's not equal to 0, would it really be logarithmic or power?
No, it's not strictly logarithmic. Okay, so you're right. If epsilon is not equal to 0, this one is not exactly logarithmic, but it has like a slight power law.
Does that ever matter?
Sorry?
Does that ever matter?
I don't think it really matters because once you have like this power law dependence, it only gets worse, as you also mentioned in the first week, right? So,
what is the physical meaning of this IR?
Yeah, so that's the point, right? That's what we are going to discuss now. So the point is that okay, so basically this corresponds to averaging over some volume. And of course, having a large effect here in some sense already means that you are averaging over a very big volume, okay? So of course that's not what a physical observer today does. He doesn't, he averages, it's a sometimes large volume, it's the observable universe, but it's a sufficiently small volume that it doesn't give a big effect here, okay? So if you want a big effect, you need to average over a volume which is much bigger than the size of the observable universe today to get a big effect here, okay?
Sorry, are you saying this formula is only valid if so zeta would normally have an index saying the momentum? So is this the limit?
Yeah, so right.
Goes to 0?
So this is the limit where there is a delta function. Okay, so let me put this in.
Yeah, but
This is the limit where sorry.
It's unrestricted. It's the soft graviton contribution.
Yeah. So here the only thing is that the momentum k is
it's not necessarily going to 0.
No, it's not necessarily going to 0. It's just smaller than the wavelength of the soft modes that you're considering.
So it should just be
K is
long
shorter
wavelength
wavelength.
compared to
Sorry,
the horizon.
did I say it opposite? Sorry.
Yeah, K is shorter wavelength than the modes.
So K is small. Sorry. So K corresponds to a short wavelength compared to the soft modes of the tensors, right?
Martin, perhaps this is the time to bring up this point. So I agree that for exactly k goes to 0, that sort of analysis should be right. Somewhere along the line, as we allow the infrared gravitons to have more and more 3 momentum, somewhere along the line that approximation becomes unreliable. Do you have any feeling for where it does become unreliable and quantitatively what kinds of modes we're talking about.
Uh,
For example, the part that interests me most is secular growth terms. Those for sure come from the ones which are wavelength at time t, which are wavelength of the Hubble radius at time t.
Yeah, so I think that, okay, so my attitude is that this guy is a conserved quantity, okay? So in co-moving momentum, the correlator of theta is strictly conserved on super Horizon scales, so there can be no secular growth here, okay? And I don't think and I think there is none here, okay? But I mean, okay, so this is something that can be discussed, of course, but I think, I think there is a number of good reasons to think that theta is conserved on super Horizon scales. Or it's not, also non-perturbative.
To apply this for our universe?
Sorry?
Are you intending to apply this for our universe where we...
Yeah, so there is a non-trivial step now in figuring out how that relates to an observer who lives in our universe, right?
Okay. But that still doesn't answer the question about where the approximation becomes unreliable. So how far out would this correctly capture the infrared graviton modes?
I think it captures okay, so here I somehow, when I put AK here, I somehow use that I evaluate this at horizon crossing for the mode K. So that, so this captures, again, the modes the soft modes that are longer wavelength than the mode of interest.
So is that
so this is evaluated. This is evaluated at horizon crossing because this is with the hidden assumption that theta is conserved on super Horizon scale. So in single field slow roll inflation, all we need to do is evaluate the correlators at horizon crossing, and at horizon crossing we can put k equal some a star. Okay, maybe I should put a star or something like that.
So you're just not even going to address the issue of when it is that approximation breaks down.
Which approximation? This approximation?
The one on the far left, the idea that for very, very long wavelength graviton modes, soft graviton modes, I certainly agree that you can do that. And as they get less and less soft, and that approximation becomes less and less accurate, when quantitatively speaking does it break down?
I think really, I mean, to very high precision, you can basically just use the horizon crossing scale for the UV cutoff here. Our explicit calculations in the inner formalism shows that
the instantaneous horizon, the time-dependent instantaneous one, or the fixed one?
The one that you basically get by putting the mode equal to some scale factor times 8 at some time where it crosses the horizon, right?
Okay.
So that's the normal procedure that that people use, right? Okay, so basically, the point is that, okay, so coming back to relating maybe to more, in the end, to something more observational, the question is basically what are the relevant soft modes and what is meant by long wavelength modes. Okay, so clearly what is meant by soft modes and long wavelength modes depends on the scale of interest. Okay, so to relate to some physical question, it's useful to define a metric fluctuation which is scale dependent. Okay, so let's say that we have a metric fluctuation where we basically integrate out all modes of a wavelength larger than 1 over q. Okay, so at some momentum scale q, we'll define a metric fluctuation where we have integrated out all long wavelength modes on the larger than this scale. Okay. Something like this. Okay. And then you can say at this scale, you can define a kind of physical momentum, okay, which you can call kappa q. Which is basically given by the usual momentum, now rescaled by this scale-dependent metric fluctuation. Okay, something like this. Right. So basically, if I'm looking at some scale q, I'm basically saying that for every problem addressing things inside the box size given by the 1 over q, modes of size larger than q is basically a redefinition of my local physical momentum in that volume. Okay. So then the point is that this argument can then be totally generalized. So if we want to write the full power spectrum, so by power spectrum I just mean that this is the 2-point function up to some delta function k. Okay. So the full nonlinear power spectrum, including all of these effects to all orders, can be captured by replacing k with the physical momentum and evaluating the 3-level power spectrum in the local physical momentum. Okay. At the scale k. Okay. So this is the claim. Okay. So basically, you have some volume of size 1 over q, and if you want to or some scale 1 over q, and if you want to capture the effect of modes longer than that scale in the power spectrum in co-moving momentum, you can just re-express the 3-level power spectrum in terms of the local physical momentum, where you have integrated out all the long wave modes. Okay. So and then of course to leading order in the expansion in the physical momentum in terms of co-moving momentum,
So that's
it will give you this
about
effect.
the sum of this whole series?
Yeah, so this will be a statement about the sum now if you include the 2-loop effects.
And are there further divergences that we're actually summing about?
Yeah, so then there will be higher, to 1-loop order there is one power in the log.
Yeah.
To 2-loop order there will be a square of the log divergences of this kind, right? But of course, the point now is that when we do observations, we don't do observations neither in the co-moving momentum or this physical momentum at the scale k at some random momentum scale. Okay. When we do observations, we do it in the physical momentum that is defined by the size of our observable volume, which happens to be the size of our observable universe. So the relevant physical momentum for observations to us is some p naught, which is some kappa q naught, where q naught is given by the size of the horizon. Okay, today. Okay, that is our local physical momentum in this universe. Okay. Oops. So
that P naught is different from the P naught up there, which is a power spectrum?
Yeah, sorry. This is a small p. I'm just not very good at typing. This is a small p. I should have chosen. This is a capital P. This is a small p. Okay. So then again, it's defined by this thing with the q naught, right? Okay, so then I think the point here is that that if you then express your power spectrum, where was it? Here, in terms of the physical momentum, p naught, instead of in co-moving momentum, or instead of this arbitrary kappa k, then your physical, your power spectrum, your nonlinear power spectrum in the physical momentum will be the 3-level power spectrum. But now, when you express kappa k in terms of p naught, the infrared divergence averages out, or is scaled out. Okay, so it becomes something like. Okay, so this is an important point. once you express your power spectrum, your nonlinear power spectrum, in terms of the local physical momentum in our observable universe, the infrared divergence is scaled out between the difference of the local physical momentum for the scale k of interest and the one in the universe. Okay. So this is infrared finite. Okay. Or IR safe.
But it only cancels for a given k.
No, it cancels for all k because Q naught is fixed for all k. Right? Q naught is fixed by the observer. You are an observer. You make an observation in this universe. Your physical momentum is defined by the observable universe in which you live. That defines your Q naught. Then for any k, the infrared part of this one will cancel towards the infrared part of this one. Okay.
It's just cancellation of the 1 over L's if you subtract those two bins.
Oh, there, yeah,
One way to put it.
But of course, there is a tiny leftover piece, which is the difference between the observable universe and the physical momentum of interest, and that's the point. And that's where the connection between conceptual issues and truly observable issues becomes important, possibly. Because, of course, if you imagine that you have a guy who is capable to observe a hierarchy which is very large between some tiny scale in our universe and the actual size of the universe, there is a leftover piece here, which does grow like now the variance of this guy. Where in the log you have the hierarchy between those two scales. Okay. But I mean, there is no infrared divergent piece here. I mean, there is only the true IR resolution of the observer in question and the physical scale that you approach. Okay. So this is somewhat similar to this, this thing that has been mentioned several times, this inclusive scattering in QED, where.
So you are already talking about the inside of after the horizon re-enter, right?
This is all modes that are now inside the horizon.
Right. Then
So-
why do we need why that structure is just kept?
Sorry?
So after the horizon re-enter, the physics will be more complex.
Yeah, that's absolutely true. I'm going to say one point about that, and then I will finish. I just want to say one thing before that, before going to really like actual astrophysics and how it actually shows up in true, matter power spectrum. I'm going just to say that, okay, it's true that, of course, for a guy who can see something like 1 over h squared equals of inflation, which is something like S, this effect will become order 1. Of course, for whatever type of inflation we have in our early universe, this is something like 10 to the 4 ethos of inflation or something like that, so that is not really an observer like us. Rather, we see something like 60 ethos of inflation. And for a guy like us, for typical scales k that we observe in the sky, this log is small. Okay. So, but there is a question of how you relate such two observers, and one point is that you can differentiate this equation with respect to the scale q, and then you can get a kind of renormalization group equation that tells you how the observable scales with your infrared resolution scale.
Well, I think that's not going to be visible to you.
Oh, sorry. Oh, the point is just.
about your formula in the upper right there. You have an integral over, is that x or k up there?
An
Do you want to write an integral sign up there, or what? On the left-hand side, you have p of p0. And
No,
then
there
you
should
have
be.
there should.
It's infinitesimal on both sides.
Yeah, there should be a.
d3 p0, and then what do you have on the right? d3 what?
Kappa k.
You also change the volume element. The metric also changes the volume element.
So there is a non-trivial question about how you relate what two different observers will see then. Because clearly, I mean, if you have two observers with different infrared resolution scale in this setup, will see different things. So then you could differentiate this equation with respect to the scale q, which was your infrared resolution scale, and then you could get a kind of renormalization group equation that tells you how the observable scales with your infrared resolution scale. So that should hopefully tell something about how you relate what a local observer like us will see. So, I mean, you imagine that you have something like a thermal inflation, as Thomas was saying. So you have something very inhomogeneous, something like this. This is your inhomogeneous de Sitter sphere or something like that, coming from eternal inflation. And then as you ask questions where you're averaging over very large volumes, or have a very big infrared resolution scale, you really see a big effect. But as you zoom in to smaller and smaller domains, it looks more and more smooth, and the effects are smaller, right? But this also means that, you know, if you take something like okay, so you can imagine that you have something like eternal inflation, and you could have some super observer who sees like 10 to the 4 e-photons of inflation. And then you could have Alice, this could be like Carol, and you could have like Alice and Bob, who each sees 60 e-photons of inflation. So we could be Alice, and we could have in a parallel universe, we could have Bob, and we could ask, well, whether Alice and Bob see the same thing. They will see exactly the same thing, because this long wavelength tensor mode inside the eternal inflating volume will rescale the local observables for A and B in this way. So if Alice and Bob then writes down what they observe at some time 60 phos after the end of inflation or whatever, then they will write down exactly the same observation. But as Cal gets to observe the full volume at some later point and synchronizes her clock globally in the full volume, she will see that there is an offset in the clocks of Alice and Bob, and there will be an observable effect to Cal. Of course, we can just scale that down to our smaller universe. So we see now we are the super observer who sees 60 ephos, and then we could divide the sky into 2, which corresponds to 50 ephos each, something like that. I don't know. Okay. And then of course, on average, this long wavelength mode compared to some very small wavelength mode question inside the horizon will average out. But if we compare the 2-point correlator measured here and the 2-point correlator measured there will be a difference. The difference will be tiny because, as we know, the long wavelength gravity modes inside the horizon, they are they are less than 10 to the minus 5. We know that by observations. So this effect, this difference in these two observations will be less than 10 to the minus 5, but it's nevertheless there, and it would be big in this total inflated volume, right?
Is the effect also proportional to the spectral index?
Yeah.
There is also an NS.
Yeah, there is also what?
NS minus 1.
Yeah, there is an NS minus 1, which I didn't account for.
Yeah, I guess what you're saying, I think, is that in the same way that in the CMB we can see at long distances some hotter regions and colder regions, if we looked at the primordial fluctuations in those regions, they would similarly be hotter or colder.
Yeah, so basically the way that people like to parameterize this kind of thing is that you do basically your thing. So you expand the trivial level power spectrum to linear order, but then you don't average over the long mode. Okay, you just leave it there. So you get something like this. Okay. So this is like a statistical anisotropy. So when you measure locally the spectrum here and here, you will see that there is a spatial difference due to the long wavelength mode. Right? But you have to have this long wavelength mode inside the horizon, and that's where the non-trivial astrophysics comes in. Because as a tensor mode inserts the horizon, it decays. It's like radiation, so it decays like radiation fluid. So it goes away very quickly as it enters the horizon. But in the matter-dominated phase, we know that structure keeps forming. So as this mode enters the horizon, it will leave an imprint on the matter that forms at that moment. Okay. So as this guy enters the horizon and structure keeps forming, as it enters the horizon, it leaves an imprint at the structure that forms at that moment. Okay. And this has been calculated in more details. Some of this procedure was outlined in a paper with Steve in 2000. I don't know. I don't remember. 11 maybe? I don't know. But it doesn't matter. But the actual astrophysical imprint on the matter power spectrum was calculated by, to great details, in a very nice paper by, let me just get the spelling right, by Dai, Xiong, and Kamiakowski. Okay, and they showed that there is exactly this 10 to the this anisotropic imprint in the galaxy power spectrum, which is a good trace of the matter power spectrum today. Okay, which is of order this, which can be maximally 10 to the minus 5 if you have maximal tensormores. And so basically, what they found, I'm soon finished. They found that anisotropy, okay, in the galaxy power spectrum, which is of order. So they found a quadrupolar anisotropy of this form, where the quadrupole is of order 1.2, and then the variance of the tensor squared, okay, of the modes inside the horizon, okay. So this is the one that is roughly 10 to the minus 5, okay. And they found that in the real astrophysical calculation, there are 3 effects that goes into this. 2 of them that I have accounted for here, basically. And then there is a third effect.
Sorry, Martin, just so I understand.
Right.
Do you mean 10 to the minus 6?
Oh, I may be using an old number. No, it's the variance. So you have some you have some logarithmic factor from some some.
I'm just asking something dumb.
Oh, sorry.
The tensor to scalar ratio is at most 0.1, so if you're talking about the usual 10 to the minus.
I think this is calculated with the tensor scalar radio of order 0.1 exactly. This 10 to the minus 5.
Okay.
But there is a logarithmic because it's the variance. There is a logarithmic some scales.
Okay.
So which makes it slightly.
I'm just saying, in the sense that the usual scalar perturbation is 10 to the minus 5. This would be 1.
Yeah, but then because it's the variance, there is a logarithmic factor also. But of course, I don't know if it's really. Okay, let me put the 10 to the minus. Okay, I don't want to get hung up in the number here.
I just wanted to make sure I understood what you were saying.
Yeah, but I think you do. I think you do. It's just. Okay, so the point was that there were three effects going into this. One is the quadrupole from the primordial correlator gamma theta, which is the basically the Maldaceno one. Then there is a projection effect, okay, which is of going into the observed coordinates, okay. Or the coordinates in which we make observation. And then there is a three non-trivial effect, which is a dynamical effect from the post-inflationary evolution. So matter clusters in the anisotropic background of the long tensor mode. So that's an extra quadrupole. From post-inflationary evolution. Okay, and I think the point is that this projection effect to go into the observational coordinates, Kamiakowski and Dai and Xiong showed very nicely that cancels the super horizon contribution from the primordial correlator, or 3-point correlator of this form. But it leaves, of course, this sub-horizon residual of 10 to the minus 5. And this is exactly what was outlined in this calculation here. Then there is an extra piece which was not captured by this argument from the post-inflationary evolution, which also has to do with this thing that tensor modes actually decay and all that. And that partially cancels actually the effect that you have from here, but it doesn't cancel fully, as you can see. From there.
1 and 2 cancel each other.
What?
1 and 2 cancel each other.
1 and 2 cancels the super horizon modes.
Super horizon.
So that's exactly what this coordinate choice also does here. I mean, that's exactly the effect. 3 gives an extra dynamical quadrupole that partially happens to be opposite sign and then actually cancel part of what comes from 1 and 2, which is the effect I predicted here. And so the actual effect is slightly smaller numerically, but it's still like of this order, right? This is that is their final result. So I think that
If I were to try and understand this physically, it's coming from graviton loops which are occurring where?
so the 3, 1 or 2.
Let's see, I think 1 and 2.
1 and 2 was basically, I think, exactly this kind of story, right?
Yeah, but I'm troubled about a point. I think it's coming from graviton loops which are occurring during inflation, have to be occurring during inflation, right?
Yeah, but I think I tried to outline how, when you use the local physical coordinates of a guy living in a local universe, then the super horizon contribution to this quadrupole scales out.
You're pulling gravitons out of the horizon, right? And so you build up a graviton variance, and the say perturbations in the scalar spectrum that are coming out of the horizon now sort of see the locally flat frame, so to speak.
Yeah, I
And
guess
so you
I'm
get
wondering
different
whether,
imprinting on each.
I guess what I'm wondering is whether or not the ultra long wavelength approximation is valid to capture sort of in between scale gravitons, which is what I think this effect is occurring from.
I'm going to talk about that.
Okay, so
We'll come in.
okay, so let me leave that then for subsequent. But I think that just one more comment, and then I'm totally done. So the point here was basically, so there is another calculation by some other people using some other coordinates where the similar effect can be captured by some tidal forces of the long wavelength mode and the short mode and all that. And sometimes all of this is referred to as projection effects, all of it together. Whatever, projection effects. And then it's said that, since this correlation doesn't exist until the tensor mode enters the horizon, it has nothing to do with primordial stuff. I think this is all a discussion, which is fight over words, but this is how you...
Maybe put that in quotes, right?
Yeah, so at least there is a physical effect, which has been computed, and some people would call it a projection effect, which is fine. This is probably what it is. So I just want to relate it to something else very quickly, just a picture. So we also computed the circumsphere of an inflating torus, just for fun. So you can compare the circumsphere here and there initially, which is something like A and E. And initially they're the same, it's homogeneous. And then after a huge amount of ethos, you get some kind of distorted torus that has inflated. And once you compute the circumsphere of the torus in different points, you do get that A is not very similar to B necessarily. Okay. So again, that is a global effect, and the idea of saying this is to try to compare to this picture. Anyway, so that was what I had to say.
One question about the strength there. That's a fractional effect on the. So this is a loop effect, right?
So actually, this effect, which is the largest effect, is not a loop effect. It's this effect, right, where you haven't averaged over the locally long wavelength interval.
So it changes the tree order power spectrum. Is that correct?
Yeah. So it gives an. I don't know if I'm saying it. I don't know if I'm responding to what you're saying, but it's introducing a statistical anisotropy in the power spectrum, tree-level power spectrum. But I don't know if you can call it tree-level at that point, but okay.
I'm just getting lost with all the powers of G and everything. If I put in all the factors of H bar and C and everything into the tree-level power spectrum, it would be H bar G times Hubble parameter squared over C to the fifth. Is this thing multiplying that, or is it?
Yeah, so essentially this gamma is something like H-O-M blank, right? So it's 1 more power of H1 plane.
So it's down by 1 more Lipton.
Yeah, so that's exactly the 10 to the minus 5 you have here.
And in the power spectrum, that would come in squared, is that right? It would be down by 10 to the minus 10, is that?
If you average, yeah, but we didn't average exactly to get the maximal effect. We didn't average over the mode.
So I think 2 things to sort of emphasize. So first, this is a real effect in the sense that in principle we could see it, although in practice it's hard. You have to go to 21 centimeter or something. And also you can write down sort of diff and variant observables that could in principle detect it on large scales. That's at the theoretical, not true observational level. So that's the first message. It's a real effect. And the second message is that if you can go to these very long time scales, it's a big effect, and it tells you that you can't really calculate the wave function of the universe in that regime in some sense. This would also apply to the case of just plain de Sitter as well. You get this after you inflate for a very long time. You get this large scale, very lumpy situation, and if you're trying to ask the question, what is the wave function of the universe, your calculation is breaking down. It's trying to tell you. So it's a big RIR
This
effect.
counts on the size of an inflating universe that someone can see, right?
Yeah, so we'd have to
Which
see
are for the-
again,
you need SE faults, right?
Yeah, that's
What's the limit on how big
I think it's curiously connected.
But it is exactly what
Yeah,
saying
so-
is that is the eternal inflation.
I think
Yeah,
it's
so-
comparable to
That's-
this.
What's the limit on how big an inflating universe you can see?
Those come in and
We can see-
An observer can only see SE faults of inflation.
S is
S is
some
the entropy
entropy.
of the final, of the reheating, just before the reheating circle.
So that's
Okay, so if I was in de Sitter and I was looking back on my past light cone and I was
The
in
point is that
perfect,
you couldn't, in the sitter you cannot measure any of these observables. You have to exit inflation. In order to be able to exit inflation, you need a slow roll potential and so on.
yeah, and
Which
if it's
doesn't
too,
allow you to
see,
roll forever.
well, why not? So suppose I end inflation and it goes into an almost, say a perfectly radiation dominated universe. If it lasts forever, I can look back further and further and further, right? Can't I?
Well, if you would enter the regime of eternal inflation and you produce black holes and so on after you.
So I see something weird in my past light cone, is that what you're saying? But I could look back.
No, I think you collapse into
You
a
collapse
black
into
hole.
singularity.
it goes out of control.
Why?
Because the fluctuations.
I'm ending, right? My universe has stopped inflating. I go into a radiation-dominated universe, and I'm just
No,
looking
the
back in the
fluctuations
past.
would be infinite, right?
Sorry, what?
The fluctuations would be infinite. So the limit that the scalar field.
Yes, that's right. So I would see big fluctuations if I tried looking back arbitrarily far in the past.
And those big fluctuations will collapse will cause
Me locally in the future?
Yeah, of course,
if
because
I'm in a radiation-dominated
you will
universe?
see them when they enter your horizon in the far future.
Wow. Well, okay.
Richard, what they're saying is that if a huge black hole had,
Exactly, that breaks down then.
come into existence very far away from us, but it came into existence and we were inside of it, that in the time aboard of the Schwarzschild radius of that black hole, we would get crushed. I believe that's
Is that
kind
what
of
you're
the
saying?
intuitive picture of
I
it.
think so, yes.
well,
So that happened in the past, but we've waited a long enough time, and there was this big fluctuation, and it crushed us. Right? If you jumped into a huge black hole, you wouldn't know it, except, pardon me, Don.
Okay.
And then a Schwarzschild time later, you would feel something,
Okay.
because there had been a big fluctuation someplace else.
anyway, I think it'd be interesting to discuss more the sort of the implications of this for the large-scale wave function, although we should let Yuko give her portion today. And
Thank you.
continue the discussion at a later time.
Yuko, that's very hard to read. Even
Oh,
right
okay.
off the
Yeah,
first
this is
row.
just my name and the collaborator's name. So, yeah. So there was a.
But write bigger for the
The
rest.
axes are also labeled.
Okay, I can just write down later. So, yeah, so there was a concern about the break of the perturbation theory. So now I'm going to talk about the case where we don't need to worry about that. So following the custom from the last week, let me give a keyword, one keyword of my talk, which is causality. So actually we were just referring that as a locality. But last week I learned that locality can mean various things. So let me, to be specific, I mean causality. So then, okay, so Martin nicely gave a review about some possible enhancement of the loop corrections of the primordial perturbations. So I'm going to talk about the one which maybe I can skip the overlap part. But so I'm going to talk about the two different stuff, which is one is infrared secular growth, so which is basically coming from the super Hubble modes is since it doesn't depend on the actually spatial dimension, so irrespective of the dimension it gets like that. So then so it gets integrating, then sorry. Is it too small?
Yeah, try to write bigger.
Okay, I will try. And I will give K cutoff. So it's just, okay, I'm going to use this figure, so let me just log K.
E alpha K over K alpha.
Yeah. So this effect is just telling you that, okay, so as the inflation goes on, the mode, which, okay, this is in this direction is super Hubble. And this one is sub Hubble. So it's just telling that, so as the inflation goes on, the mode, which are located outside of the Hubble scale, becomes more and more. So then it's a somehow simple effect, this one. And there was another one which gives secular growth. That is from the time integral. And I think, okay, so since Martin didn't tell about that, I can mention somehow a bit. From time integral, maybe it's too small. Time integral. Okay, so imagine that let's compute some loop corrections or non-Gaussianity, whatever, some nonlinear corrections. Then the action is typically like dt dx times determinant, so which is typically a to d. So okay, so for simplicity, let me consider the case where causality holds. Even in such case, so this one is basically the Hubble scale. So it's like AD. So the volume we are integrated basically logarithmic. So in case there are, okay, so let's consider, okay, some vertex are inserted in x1 and x2. So in case these are, two different vertices which have.
Yuko, I'm getting lost. You're considering a Feynman diagram where there's two vertices.
Right, two vertices are inserted.
Integrating over them.
Yeah, then in case long-term separation are not suppressed, then just basically, typically, this integral about time can give logarithmic effect. So since this is coming from the time integral of the all modes, so it's not only the infrared effects. I think this one is more complex one. So then, what I'm going to claim right now, so first is that if we keep causality, then both of them do not appear. So this is the first one I want to claim. And I'm gonna say this is a.
Is this generic or is this for single field inflation?
This is only for single field. So, and if I can say second keyword, which is gauge invariance. So if I preserve gauge invariance in a causal sense, both of them disappear. So then, as the last point, I'm going to talk about a bit. I'm going to mention about the observables, which have discussed.
Could I ask about the claim a little bit more? Both of them disappear in what? In what kind of variables?
Okay, so
all correlators.
Gauge invariance is preserved. Quantity which preserves gauge invariance.
And you'll give us an example of such quantities?
At the last point, I'm going to discuss. Okay, so causal gauge invariance. So when we take into account the causality, the gauge invariance, the meaning of the gauge invariance becomes different in the sense that, okay, so to compute the gauge invariant variable, the simple way is to reduce the number of the variables. So then let me fix the gauge conditions. However, when we consider the causality, we can observe only the finite region in the universe. So that means that we can fix the gauge only within the path right cone. So because of that, okay, so we are here. Since we cannot fix the gauge outside of the path right cone, so there is always ambiguity because of as a boundary condition of the light cone. So that happens when we consider the flat slicing and also the zeta gauge. So then, since we cannot, okay, so this is.
Are you making the same point that Martin was making? He was describing it as a condition of the observer.
Right, I'm rephrasing in a different language to connect to the observable issues.
Okay.
And Martin's degrees of freedom appear as one of these residual gauge degrees of freedom. Okay, so to be more explicit, so for instance, in zeta gauge, the shift, so as Huang formulated, the constraint equation gives something like that, theta dot plus. So since it is an elliptic form, so we need to, in order to determine, the solution of Ni, we need to solve this elliptic type equation. For that, we need to impose the boundary conditions. But since we can see only, we are just concerned with only this finite region, and then they appear as, degrees of freedom in what kind of boundary condition we impose. So particularly that what we get is that in this case, is like, just naively, it's like something like that. So we can change the spatial coordinates which satisfies the Laplace equations. So, and one of the important stuff is that at each time we have this residual gauge degrees of freedom. So this one can depend on time. So to be more explicit, let me pick up only the important ones. So which is minus st.
Larger.
xi minus st. This is tensor xj. This one is tensor. So it's one of those. So my claim is that when we construct a quantity which is invariant and such gauge degrees of freedom under such gauge transformations, we are safe from this to enhancement of the loops. And we don't need to worry about the break of the perturbation.
In your formula there, do you have two different S's?
Yeah. what is T?
With a little s and a big S. It's
Yeah.
fine.
This is the zeta and the gamma, right? From
Right.
the previous talk.
C.
Okay.
So basically, so this two time-dependent variable can change zeta to zeta minus s t. It can depend on time.
So I'm confused. Are you saying that if you're looking back, inside your horizon, that you can't see the kind of logarithmic effect that Martin was just discussing, or are you
So
saying
I'm just
that
talking
you...
about only about the so the effect, which comes from the only about the a causal effect, in that sense, which
That's
is
the causal
basically the
effect.
superhyperbolas. So I'm not talking about after the horizon re-enter.
Okay, you're saying I can get rid of the basically the IR cutoff dependent effect that is outside of our horizon.
Right.
Yeah. Okay.
Yeah, so I don't think what I'm going to say. Okay, so what I'm going to say is basically quite similar to Leonardo says, and I don't think it's contradict to what Martin says. Okay, so basically, so what I do is just to construct the quantity which is invariant under this, gauge transformations. But okay, so constructing such a Gauge-man quantity is not easy. So here, so what we could do so far is just construct a quantity which is invariant basically under these transformations, because that is important to address the infinite issues of curvature perturbation, scalar and tensor perturbations, which is zeta t. Sorry. So let me introduce.
So sorry, I guess I missed it when you said what boundary conditions you were going to impose. Are you basically saying you allow anything on the boundary of your visible region, or what?
What I'm saying is that since we cannot impose gauge conditions outside of the light cone, because of that ambiguity can affect on even inside of the light cone through the boundary conditions of the light cone.
So what boundary conditions are you imposing?
I'm not imposing the boundary condition. I'm saying that the observable quantity should be invariant under the change of such boundary conditions.
Right, so you're allowing any solution to the elliptic equation that induces whatever on the
I'm
boundaries.
allowing even the non-normalizable change of the coordinates.
Okay.
That's the point, actually.
Yeah.
So then what I'm going, so then just so this is the window function in the light cone. So yeah, and I forgot to mention one thing, which is so in this talk I'd like to mention one thing which is about the restriction of the inflationary initial states. So I suppose that if we require the invariance under the gauge invariance with causality, I think the possible inflationary initial states restricted. So this point I think has not discussed so far. So I'm going to talk about that a bit. So then, so what minus? So the definition is recursive. Okay. You can't see? Sorry. The rest cannot see.
I think this is okay on this board. Maybe we could not use the last board there.
Okay. Yeah, so for the same thing, okay, so zeta bar is this thing, and what I'm going to compute is zeta Tf. It's an end of inflation. T TF minus zeta bar TF. And this thing is invariant under this transformation. So once we compute such quantities, since we can shift so for simplicity I wrote only the scalar perturbation, but the same thing for the tensors.
Sorry, what is WLC?
This is a Windler function which has support within the path right cone. So it's
what
like.
What does that mean? It's just a function of space, right? The light cone's a function of space and time.
Okay, so. Sorry, thank you.
But I'm still confused about that.
But maybe this is.
Are we doing an integration over time as well?
No. This is just giving the size of the.
Yeah, but I don't know what the formula means. Is it an integral d3?
Okay, so at each time there is a size of the light cone.
Yes.
Then just basically smearing within the light cone.
But is C evaluated inside the light cone?
This is the typical size of the light cone, which is like from current to T dt. This is just the background.
So there is an integration over time as well, right?
There isn't. So maybe it's better to put index T here.
I'm not sure I understand what the formula
Right, but
says.
Your integral is integral d3x with the upper limit is L.
Okay, yeah, that's right. Yes, sorry.
And you're saying the upper limit is L the way you define it over there.
Right. Okay. So when we compute this quantity, okay, so this quantity.
I'm sorry, I still don't get it. So T is which time? T is.
T is each time. So at each time, we can compute. Okay, so let's forget about something complex. You can take average, spatial average at each slicing.
Let me see if I understand it. There's some observer up at the point of that light cone, right? And
okay, yeah, we are here.
Looking back in the past,
right?
At zeta.
At some point, there is an end of inflation. So we are just now. I'm just computing here.
Okay. All right.
Okay. So, since this quantity is invariant under this transformation, so basically, so I can use this symmetry such that I can use this symmetry such that this term cancels.
I'm sorry to be quibbling here, but the light cone is really a dynamical thing. Do I have to take that into account? Does that matter?
Okay, so to be more precise, we need to take into account such a dynamical effect. But what is important is just it's bounded of this order. And as far as the perturbation is kept small, it's basically consistent. We can talk about it later if you wish. Okay, so since we have a.
What about the far past? I mean, where do you cut off this region in the?
Okay, yeah, I'm coming back to that point later. And before that, let me mention one thing. So, in order to compute the quantity which is invariant under this transformation, one thing is that I need to compute the operator which is invariant under this transformation. But I also need to take an initial state which is invariant under this transformation. And here we get the restriction on the initial states of the inflationary universe. For instance, initial states. For instance, as a simple example, let me consider the case. I think I will need just, may I speak 10 minutes, 5?
Yeah, 5 would be good if you can. Yeah.
Okay, so maybe, okay, I will try. So for simplicity, let me consider the case where we turn on the interaction at some finite time, initial time. Then afterwards we have, so before that we don't have interaction, and afterwards we turn on interaction, if you wish, gradually. Then in this case, what we found is that the case where this symmetry is kept is only the case where the spectrum of zeta is exactly scale invariant for all k. So which is not Hadamard. So this means that if we turn on the interaction at some particular time, then so the Hubble scale at that time becomes some peculiar scale. So then unless we take a very strange states where the spectrum is exactly scale invariant, we cannot keep that scale invariant condition. So it's basically saying that the same I think it's the same condition as the case where we get the consistency relation. So the consistency relation of the bispectrum we cannot get the consistency relation if we change the initial states. So anyway, so the invariance under this symmetry restricts the possible initial states.
I thought the consistency relation was true in Bunch-Davies vacuum. Is that not correct?
It is true for Euclidean vacuum, but I think if we change.
Isn't it true in Bunch-Davies vacuum? Like if I had, suppose I had a constant epsilon inflation, which was epsilon not equal to 0, wouldn't the consistency relation still be true?
What I meant is that okay, so since we are considering inflationary setup, so maybe I can say adiabatic vacuum. So when we take adiabatic vacuum, we can get the consistency relation. But if we change, okay, let me consider the Bogoliubov transformation, then in this case, we don't get the consistency relation. Mm-hmm. It's basically because this scaling symmetry is broken. But this is a side remark.
Does this restriction on the initial state arise from trying to take the past light cone all the way back to minus infinity?
Right. So then in order to get this symmetry, then what I can do is to send t initial time to minus infinity.
Only if you have.
Right. So then coming back to Tom's point, so okay, so this time integral issue becomes more severe. So then what is needed is that to regulate, so this time integral should be convergent. But actually it is the case. For okay, so then I think so the only case where we can have a regular this limit is the case we impose the boundary condition of the Euclidean vacuum. So then let me take a Euclidean vacuum where the time path is rotated towards the imaginary axis. In such case, so as I mentioned, in such case we can preserve this symmetry. So then using this symmetry, I can change the homogeneous part of the curvature perturbation and tensor perturbation. And then by using that, so this part can be removed. And also, so this is infrared limit is this way and UV is this way. Then when we take the boundary condition of the Euclidean vacuum, so unless 2 points, okay, so I'm writing this as some wiki. So I'm writing which mode contributes to this Wyman function. Then since this part is suppressed, and with the boundary condition of the Euclidean vacuum, unless x1 and x2 are mutually light-like related, these UV contributions are suppressed. And this can be shown by using the boundary condition of the Euclidean vacuum.
What does it mean to be light-like related if they're in the Euclidean vacuum?
Just means that x1 and x2 are no related.
You're not in Euclidean space, you're just in the Euclidean vacuum, is that it?
Right. So then what is contribute is only around the Hubble scale. So this means that imagine that the x1 and x2, T1 and T2 are largely separated, like here or here. In this case, so this Wyman function should be suppressed either UV or infrared. So because of that, we cannot have long-term separations. That should be suppressed. Then this goes away.
let's see, you meant to say that is suppressed under those assumptions, is that correct?
Under when this symmetry is preserved, which is requested from the gauge invariance with causality. And let me finish my claim. Okay, so this is what we have done so far. And I want to come back to the original point, which is observables. So about the connection to the astrophysics, Martin gave already discussed. So let me just talk about here. I just mean that the quantity, so gauge invariance with causality. How to construct such quantities? And actually, so I cheated a bit because so I mentioned that when we just preserve the symmetry under this transformation, we are safe from these two enhancements. But actually, it's not true because so the shift has these non-local operators. So other than these degrees of freedom, there are some effects which can mediate the inference from the outside of the light cone. So actually, in order to compute the truly infrared regular, or the one which doesn't have that secular growth, we need to provide the gauge invariant quantity about all of the degrees of freedom which describes the inference from outside of the light cone. And for that, we considered. So this is the bad example, actually.
How can there be any influence from outside of the light cone?
Sorry?
How can there be any influence from outside of the light cone? Are you using the Schwinger-Keldysh formalism?
Yeah, but in this, I don't know if it is just the issue of these gauges, but these are non-local gauges. So I think in order to reduce the degrees of freedom.
It's the interactions. It's that the constraints involve solving an elliptic operator, and
right.
that gives rise to terms.
So the action becomes non-local. Anyway, so let me finish my claim. So then, so what we did is, what we have considered is that at each time slicing, so we can consider the, say, 2-point function which are connected by the geodesics. This is Euclidean geodesics. And then let's take, say, the scalar, which is connected by geodesics. Then this can be invariant and basically invariant under all the gauge transformations.
Well, that's something one can try to define as a gauge invariant.
Right.
It's not clear that it's simply related to what we see. What we see is looking back. We
right.
see angular scale.
Okay. So I'm just talking about. I'm not talking about. So how can I say not observable? I just mean that.
Actually, we coined a term for the Q observables.
Right.
They're quantum observables, but they're you don't want to confuse
I don't
people
mean
who
that,
really do observations.
Measurable quantity.
Yeah, Q observables.
Right.
Anyway.
Yeah, just to connect to the discussions in the first week. Mm-hmm. So then this one will become so the gauge invariance, gauge invariant quantity. However, so as you pointed out, there could be some, since this is a non-local quantity, so there could be some problem in discussing UV renormalization, as Richard pointed out. So yeah, I don't have clear answer on that. But yeah, I think, so I don't think, so since there is no concrete quantity which can be invariant under the, and which can be gauge invariant. So I think, yeah, to make it, to show that in some concrete, for some concrete variable, then it's important to keep on discussing about this constructing.
I guess it depends on how much you're willing to use the structure of the initial state, the fact that we release the universe in some prepared state at an initial time.
Mm-hmm.
Are you willing to use that or not?
Initial state?
Yeah,
Sorry?
so trying to build a gauge invariant is really hard if you don't have any structure to build it off of. Are you willing to use the fact that we released the universe on some initial 3 surface in prepared state? Okay, then I think you could define a 3 surface based on how far you've evolved from the initial state, and you could fix at least the 3 surface, basically the same way that everybody is doing it.
Okay.
You can use the inflaton to do that.
Yeah, right. Yeah. So define some kind of, it doesn't even have to be the inflaton, even in pure gravity, just any kind of a scalar clock.
But this correlator you're defining here, you're saying this is a candidate for a CGI observable?
Yeah, this is a CGI. However, this is a non-local quantity.
Yeah.
So then it may create.
Okay, but let me just understand that. So then that's connected by some space-like geodesics?
Right.
But isn't it hard to find space-like geodesics that connect points that are separated far compared to the horizon?
Not if you constrain to within the surface. It's
Right.
A
It's a Euclidean.
Okay.
geodesic.
So within this time slicing.
Right.
Yeah.
Also,
So unless they are
you're thinking of fixing the 2 points and then trying to find a geodesic between them. If you actually built it, you'd start from a point and then go off in one direction, go off in another direction. That's guaranteed to work, at least perturbatively.
Yeah, unless they create some caustics.
Wait, not if you're outside the horizon.
Even if you had caustics, you can evolve the thing forever along the spatial, along a 3 surface. So you could.
No, if you stay in the 3 surface, you're fine. But if you're looking for a 4-dimensional geodesic that's space-like, you can't go further than the horizon size.
Okay,
Isn't it
so
only
stay
important
on the
for
3
you that
surface
it's,
then.
I mean, if I understood correctly, you've got this background structure that you're only concerned with the gauge, the spatial gauge on this preferred foliation.
Right.
So the issue of a space-time geodesic doesn't
Yeah.
come up.
Yeah, what I'm concerned is the compatibility with CGI and UV regularization.
So did I understand the conclusion correctly that you said basically conceptually you're claiming if you follow this procedure of causal gauge invariant instruction, there won't be any IR effects. However, to actually implement it, you need gauge invariant observables, and you don't know how to construct one that you know how to renormalize or something like that you've explicitly.
Yeah, maybe I can say one thing. So what I know about UV renormalization is that so the UV divergence is coming from only the case where the 2 vertices are light-like related.
Okay.
So that I think nothing but the coincidence limit. So in this sense, I think that could be local quantities, but zeta is already non-local gauge. So I think in order to say that, we did a UV renormalization, I think we should introduce a counter term in a covariant way. So yeah, for that I agree with Richard that we are not, at a level where,
But at the issue about, say, each of the factors of the Ricci scalar in that correlator you wrote, so would you just say there, you're just talking about a perturbative implementation of that observable, and you don't have to deal with operators multiplied at the same point? Or what? I mean,
point means
no, each R separately is a nonlinear function of the metric if you were to calculate it exactly.
Right.
So I presume, so is the idea to implement what you're saying, you don't need to calculate it exactly, you're just perturbatively evaluating R, and R itself is a linear function of your field?
This one is nonlinear function.
Okay, so then it seems like the issue of...
Right. This is actually, so this argument applies to basically, as far as perturbation theory is fine, this argument applies to all order in loops.
Yeah.
So unless the amplitude gets... So actually, so as I mentioned, there is a suppression in long-range correlation. So then, unless, so as we go to the, early stage, the amplitude becomes bigger and bigger. So then unless that is overcome by this suppression, then everything is fine.
Okay, so I want to ask some questions here. So if I looked at just an endpoint correlator, say h of x, h of y at the same time, and I evaluate them, then you would say, or gamma ij of t and x, gamma ij of t and y. you would say that I should, or at least I could, see secular terms in that, but that if I formed it into a gauge invariant quantity, if I put together a lot of different Green's functions to make it order by order gauge invariant, then all the secular growth would go away. Is that the statement?
Right. As far as we keep this gauge invariance, we don't see.
But it seems like in your analysis you only needed that gauge invariance, and enforcing that much gauge invariance is a lot easier than enforcing full gauge invariance.
That's the point. I cheated a bit. So, yeah, in order to cancel the super Hubble contributions, what I needed is just this symmetry. But so here, actually here, in computing here, I'm assuming that the interaction vertices are confined within the light cone.
Yes, right.
But it's not preserved as it is in these cases. So I need to choose, change the boundary condition so that the interaction vertices are confined in the light cone. And that requires another kind of the gauge transformation. And this one is not, I actually erased, and this one is not invariant.
So if I did the calculation on de Sitter, so I didn't do all of the ADM stuff, and I did the calculation in a covariant gauge on de Sitter, so I didn't have any non-local constraints that I was eliminating, and I was dealing with covariant propagators, and I was using the Schur-Keldysh formalism, would you?
But you mean in exact de Sitter with tensor perturbations?
Yeah. And I was looking at an endpoint correlator of Hij.
I suppose for the tensor perturbation in exact de Sitter, there will be similar problems.
Similar problems?
Yeah, with non-locality. But I think that in the same way, I think we can solve the issue.
Well, by doing that, or
by constructing the quantity which is invariant under this.
See, enforcing that invariance is a lot easier to do than enforcing the full invariance. I think that much I could do a calculation on to just decide the issue pretty quickly. Enforcing one of those things would be, well, I don't even know how to renormalize it.
Maybe we could continue this after, but I think, Tom had a question.
Yeah, I just wanted to rephrase possibly what you said about the interaction of IR and UV. So the thing that would bother me about the kind of thing that you're proposing conceptually is that you can have things which are pure gauge modes every place except within some distance, 1 over epsilon from the light cone, and then do something physical right out in that region. Okay, and unless you've dealt with the UV problem right along the light cone, you can't distinguish. Those are real physical modes, but they look like gauge transformations in any sort of region that's finitely separated from the light cone. So when I say this is a general problem in gauge theories in the continuum, that when I try to make something gauge invariant but also have a boundary, then I introduce new observables on the boundary that are physical until I'm willing to consider the region outside that boundary. And you're trying not to do that in order to eliminate these IR divergences. So is that a way of rephrasing the problem that you...
Yeah, about the concern about UV.
About the UV.
Right.
Yeah.
Thank you.
Okay. Any other comments or questions? Okay. Thank you.
Thank you.